All right, so the next video in chapter 12, we're going to talk about Bernoulli's equation, which is probably the most important principle we're going to come across when in terms of fluid dynamics. Okay, so Bernoulli's equation. So Bernoulli's equation describes the streamline or laminar flow of an ideal fluid. So remember, laminar flow or streamline flow, I showed a video in class. So that's sort of where the simple type of flow, not a turbulent flow, and it's for an ideal fluid. So ideal fluid means it's incompressible, so liquids effectively, and there's no viscosity, so no resistance to flow. And what it looks like, so the pressure of the fluid at one point plus 1/2 times density times the speed at that point squared, plus the density times acceleration due to gravity times the height at that point equals pressure at point 2 plus 1/2 rho v2 squared plus rho gy2 squared. So that's Bernoulli's equation. And really, if you stare at this hopefully looks a little bit familiar because it's really just conservation of energy, right? This 1/2 rho v1 squared, well, that looks suspiciously like a kinetic energy. And in fact, it almost is, except, well, instead, kinetic energy is 1/2 mv squared. This is 1/2 density times v1 squared. So really all we've done here is we've just divided by volume, right? So we've got mass per volume instead of just mass. And then similarly, this density times acceleration due to gravity times the height, well, that's really just gravitational potential energy per volume again. And actually the pressure, well, pressure is force per area. And well, if we divide by volume, actually what we get is work. So the pressure is related to work. The 1/2 rho v squared is related to kinetic energy, and the rho gy is related to gravitational potential energy. Okay, now in the case that, so if we have fluid flow at a constant depth, so basically what this is saying, if we go back to our equation here, so it says, okay, so what happens if the depth or the height doesn't change? So effectively, y1 is exactly the same as y2. Well, really what that means is we can just cancel out those terms and the equation gets a little bit simpler. So we have pressure 1 plus 1/2 rho v1 squared equals pressure 2 plus 1/2 rho v2 squared. So the gravitational potential energy terms just went away because our height isn't changing. And this is known as Bernoulli's principle. And again, one way to think about this, so is since the two sides have to balance out, what this really says is that, oh, if your speed increases, so if V2 gets bigger, well, then the pressure has to go down, right? Because they have to balance out. So the speed, as the speed of a flowing fluid increases, the pressure of that fluid decreases. Okay, so let's do a quick example. So in the previous video, we looked at the water flowing in a hose with different size, with a specific size of a nozzle. So now let's think about the pressure, and in particular, so the speed of our water went from 1.96 meters per second in the hose to 25.5 meters per second in the nozzle. So let's figure out the pressure in the hose, given that the pressure in the nozzle is 1.01 times 10 to the 5th newtons per square meter, right? So that's just atmospheric pressure, and we're going to assume the height doesn't change. So, as with most fluid dynamics problems, we're going to start with Bernoulli's equation, but conveniently, the height doesn't change, which means our rho gy terms are the same on both sides. They go away, and we're left with Bernoulli's principle, which is the second equation down here. So, and again, we have to decide what do the ones correspond to and what do the twos correspond to. So let's say the ones correspond to the hose, the twos are going to correspond to the nozzle. So we're looking for the pressure in the hose. So we've got pressure 1, or pressure in the hose, is going to be 1/2 times density. Well, if this is water, density is going to be 1,000 kilograms per cubic meter times the speed in the hose squared. So the speed in the hose was 1.96 meters per second squared. And that has to equal the pressure in the nozzle, which we're told is 1.01 times 10 to the 5th pascals, or newtons per square meter, plus a half times density, which is still 1,000 kilograms per cubic meter, times speed in the nozzle, which was 25.5 meters per second squared. So P1, and let's work out some of these numbers. So on the left-hand side, so I've got a half times 1,000 times 1.96 squared. So that's 1921 pascals. And that's going to be 1.01 10 to the 5th pascals plus a half times 1,000 times 25.5 squared, which is 325,125 pascals. So now solving for P1, so pressure in the hose. So I take 325,125 plus 1.01 times 10 to the 5th, and then I need to subtract 1,921, and it looks like I get pressure in the hose is 424,000 pascals, or newtons per square meter, which makes sense because remember, the pressure and speed are inversely proportional. So the speed in the hose, is less, so the pressure in the hose has to be more.